Hi, everyone. My name is Srinivasan Raghunathan. I'm a postdoc at the University of Illinois, Urbana-Champaign. And today, Marius Millea, who is a project scientist at the University of California, Davis, and I will be presenting some of the recent and latest results from the South Pole Telescope collaboration. So maybe the next slide. Right. So on this slide, we have some snapshots about the results that we're going to present. So on the left, you see the recent constraints from the kinematic SE signal. So this is constraints on epoch of reionisation. So this is the first constraint on epoch of reionisation using the non-Gaussianity of the KSE signal. So that's the one on the left. Then in the middle panel, you can see the constraints that we expect from the upcoming result of SPT 3G. So these are 2 years of data. So these are the improvements in Hubble constant, and you can see that the constraining power is now pretty close to what we can actually get from Planck. So then we will also mention some of the forecasts that we expect for the full SPT3G survey, where, as you can see, we expect roughly a factor of 2.5 improvement on parameters like Hubble constant, neutrino mass, and dark energy equation of state compared to Planck. Okay, so this is the outline of our talk. So we'll briefly introduce the standard model of cosmology, then go into cosmic microwave background, explain the primary and the secondary anisotropies. Then we will also say why these measurements are interesting and how South Pole Telescope contributes to all of these things. In particular, we'll be talking about the recent constraints on reionisation using KSE and the upcoming constraints on cosmology and structure formation using primary lens CMB. Finally, finish with expectations from the full SPT3G survey. Okay. So here is a very, very brief review of the standard cosmological model. So in the beginning, there was inflation, which is an accelerated expansion of the universe, followed by the Big Bang. So initially, the universe was extremely hot, dense, and as a result, opaque. So photons cannot travel freely. So whenever they try to travel in a straight line, they get hit by a free electron. They get hit by an ion because the universe is very ionized. So there are free electrons everywhere. So the photon path keeps changing. So it took around 400,000 years after the Big Bang for the universe to cool enough. That was around redshift 1100, 400,000 years after the Big Bang. So the temperature was cool enough that neutral atoms could form. And it is at that epoch, the CMB photons started to free stream towards us. So this epoch is called the surface of last scattering, or it's also called the epoch of recombination. So then later, the universe expanded further, it cooled further, but it started also forming structures and stars. And then later, as time progressed, we start to have bigger and bigger structures like galaxy clusters and superclusters that we see today. So you can put all these things into these bullet points that are given here. So it was inflation plus the Big Bang initially. Structures grow hierarchically, meaning smaller structures form first. They combine to form larger structures. Gravity is very well explained by GR. The universe that we live in is a flat universe. And the universe that we live also contains dark matter and dark energy besides the normal baryons. So these are all the things that the observations tell us. Of course, we don't have the smoking gun evidence for inflation yet, which are the detection of the primordial B modes, which is a goal that everyone in the field of CMB is working towards in the next decade or so. So what is cosmic microwave background? So one of the strongest evidences supporting the theory of Big Bang is the discovery of the cosmic microwave background. So like I said before, initially the universe was hot and dense. So it took around 400,000 years for the universe to become neutral, only after which the CMB photons free stream towards us. So that is what the schematic is showing in the top. But then later, the universe was very neutral, but then as the first stars and galaxies formed, the universe started to reionize again. So that is the next epoch that's marked in the figure. So it's the epoch when first stars and galaxies formed. So that's the epoch of reionization. So what is CMB? So CMB is basically it's the remnant radiation from the Big Bang predicted in 1940s, accidentally discovered 20 years later by Penzias and Wilson. It is an extremely homogeneous and isotropic radiation, meaning it looks pretty much the same statistically any direction that we look. And it has a black body spectrum peaking at around 2.7 Kelvin. But the CMB is also polarized, and this polarization is due to Thomson scattering at the time of recombination. But CMB is only partially polarized, roughly around 10%. And the other important thing about CMB is that CMB is the most distant light that we can see in any direction. And as a result, the CMB, the free streaming CMB photons, interact with everything that we know in the universe, namely galaxies and galaxy clusters. So these interactions, they'll lead to this additional anisotropy in the CMB called the secondary anisotropies, which are also excellent probes of cosmology, as you will see in the talk. So how are we measuring CMB? So these are some of the experiments that have successfully measured CMB. There are also others, but I'm only listing some of them. So the map that you're seeing here is a map that was actually observed by 3 different satellites. So first it was COBE, which was launched in 1990s. As you can see, the angular resolution of COBE is actually very poor. It was around 7 degrees or so. But COBE did manage to discover the anisotropies on the CMB, did manage to observe the anisotropies of the CMB. So 10 years later, WMAP was launched. You can see the improvement in angular resolution. And then 10 years later, Planck was launched. And you can see the improvement in resolution compared to COBE and WMAP. So Planck had something like 5 arc-minute resolution. But we also have other experiments from ground, like South Pole Telescope, which is the South Pole. So South Pole Telescope is a very, very high angular resolution CMB experiment, roughly 1.2 arc minutes at 150 gigahertz. So then we also have Atacama Cosmology Telescope in Chile, which is roughly a 6-meter telescope, so something like 1.4 arc minutes angular resolution. Then, of course, we also have the Simons Observatory, which is upcoming in Chile, and then CMBS-4, which is planning to start in the next decade, both from South Pole and from Chile. So why is CMB interesting? So one of the things that we do as cosmologists is to map the CMB, and then we make we basically compute the power spectrum of the CMB. So power spectrum is nothing but the 2-point correlation function in the real space. So the Fourier space version or the spherical harmonic space version of 2-point correlation function is called the power spectrum, which is shown here. So the 3 colors are for 3 different power spectrums. So red is for temperature, blue is for E mode polarization, and green is for B mode polarization. So the horizontal axis on this plot is the multipole, which is actually the inverse of the angular scale. So if you're looking at the right side of the plot, you're looking at very small angular scales. And if you're looking at the left side of this plot, you're looking at very, very large angular scales on the sky. And the vertical axis is the power. It's also the variance in the map, okay? So like I said before, CMB is only partially polarized. That is the reason temperature is much brighter than polarization. So the most important thing that I want to share about this plot is that different parts of this power spectrum are sensitive to different things about our universe. So for example, particularly for ground-based experiments, since we have high angular resolution, we are mainly probing the small scale information. And when we are probing the small scale information, we can actually learn a lot about light relics or neutrinos. Okay, so different parts of the power spectrum are sensitive to different physics, and measuring these will give us a very, very good knowledge about cosmology. So that was theory, and this is basically putting all of the data points measured by different instruments on the power spectrum plot. Okay, so it's basically the same plot, but showing all the measurements that has been made by different instruments. So the amazing thing about this is that all of these instruments, they align really well with each other. And more importantly, you see these curves that are running through these data points. And I would like to emphasize that this curve or these curves, they're actually not a best fit for all of these data points. So these curves are actually the ΛCDM prediction. And it's amazing that all of these instruments have measured those things accurately. So this is great. So if all is so well determined, why do we have to build new surveys? So even though we have measured this, we have this ΛCDM model, it is actually a mystery that this model works, because there are so many things that we are yet to understand. For example, we don't know much about the properties of dark matter or dark energy. We are yet to discover the primordial gravitational waves. We have limited knowledge about neutrino masses. And then, so that's the first thing. The second thing is that different probes of cosmology actually give us different results for some of these parameters. So there are tensions that exist between different probes. And these are the reasons why we would like to build new surveys and measure these, even more accurately. So what are these tensions? So are these tensions real physics or systematics? They could be anything. We don't know yet, but that's what our next generation or the current measurements will tell us. So what I'm showing on this plot is basically the measurement of Hubble constant made by Planck, which is shown in the bottom, and then made by SPT3G, the first year of SPT3G, which is shown in the top. So you can see both SPT3G and Planck are consistent with each other. And then we also show the expectation for the upcoming release from the first 2 years of SPT3G. So you can see that the error bars are shrinking. And then when we combine all SPT3G from 2019 and 2020, so the first 2 years of observation, you can see that the error bar on Hubble constant is now becoming very comparable to Planck, which is great. But the thing that I would like to emphasize here is that there is also this gray band that you're seeing here, which is actually a direct measurement of Hubble constant made using supernovae and Cepheid variables. So as you can see, the CMB measurements agree well with each other from SPT3G and Planck, but they don't agree with the direct measurements of Hubble constant. So there is something that's different between these two measurements. So this measurement can actually be something real, or it could be a systematic in one of these, observables. So we don't know these things yet, and the tension seems to grow with subsequent releases from different CMB instruments. Okay, so that's something that we would like to fix. So here is an example for another tension. So this is tension in structure formation. So what I'm showing here is it's a measurement made by ACT lensing measurements. So what you're seeing here is we call it the S8, which is basically a product of sigma 8 and omega matter. So as you can see, the inferred value of S8 from different CMB instruments shown in green and red, they agree well with each other. But the ones made by galaxy surveys shown in blue, they are slightly lower. So here the tension is not as big as what we saw in the previous slide, but it seems like the tension is actually growing. So again, this could be real physics because these measurements are probing different scales, or this could be a systematic. So the upcoming results from SPT3G will be able to shed a lot of light on these things. So that's why these measurements are interesting. So like I said, the previous slide was made with CMB lensing. Also, CMB lensing adds a lot to Hubble constant measurement. So the CMB lensing is one of the secondary anisotropies of the CMB. So what exactly are these? So let me go into those things now. So like I said before, small fraction of the CMB photons interact with intervening structures in the universe, giving rise to the secondary anisotropies of the CMB. So since they interact with every structure that we know in the universe, they are excellent probes of structure formation. Okay, so among other probes like galaxy surveys, for example. But to measure these secondary anisotropies, we need really high angular resolution. So high angular resolution is crucial to probe the secondaries on the small scales. Okay, so that's where South Pole Telescope comes into picture. So South Pole Telescope is a 10-meter telescope, 10-meter diameter telescope at the geographical South Pole, observing the millimeter wave sky in 3 different bands. So 90 gigahertz, 150 gigahertz, 220 gigahertz. So 10-meter telescope. So at 150 gigahertz, the angular resolution is roughly 1.2 arc minutes. So here is a picture of the South Pole Telescope. So this is a really beautiful picture taken by our winter rover, Aman Cholsky. So what you're seeing here is basically a time lapse of an eclipse that happened. You can also see the beautiful Southern Lights Aurora Australis. So this is a really great site to do millimeter wave observations. So in the next few slides, I would like to show why South Pole Telescope is great to measure these small scale information. Okay, so on this plot or on this slide, I'm showing the data from WMAP. So it's a real data, roughly 30 square degrees of the sky. Okay, so we can see some dark spots and cold spots. So these are all CMB, primary CMB measurements. So if you look at the same region with Planck, so you can see if I go from WMAP to Planck, so you can see the angular resolution improves significantly. And then if you look at the same region with South Pole Telescope, so let me flip that again. So WMAP, Planck, South Pole Telescope. So you can see that the resolution has improved significantly. The noise level has come down significantly. So that's so this map is from a previous generation of SPT. So it's called the SPT pole survey. But the current measurement made by SPT3G is roughly a factor of 1.5 more sensitive than SPT pole. So the majority of the things that you're seeing, the large scale information, the big dark spots and cold spots, so those are all primary CMB. So those are all cosmic microwave background. But besides these cosmic microwave background signal, you're also seeing these white spots. So these white spots are actually signals coming from galaxies in the universe. So these are radio galaxies, quasars, AGNs, and also dusty star-forming galaxies, which emit in the same millimeter wave band. So these are contaminations when we do cosmology, but these are real signals for astronomers. So these are the white dots, but now we also see these dark spots, right? So the black dots. So these are actually galaxy clusters. So these are clusters of galaxies. So the reason they appear dark is because of this effect called the Sunyaev-Zeldovich effect. So we use this effect to actually do a blind cluster survey with CMB telescopes. So you see, we don't just observe CMB, but we also observe all of these small scale information. Okay. So the science driver for SPT is very, very vast. Okay. So here is a list. And in this talk, we are going to only focus about the first two things. So cosmology using primary and secondary anisotropies of CMB, and probing reionization using SPT. Okay, so these are our latest results and some of the upcoming results. So again, just want to say what exactly are these secondary anisotropies. So I said previously that these are excellent probes of structure formation. So there are many secondary anisotropies. So first one is gravitational lensing and kinematic SE. So I will explain those things in detail in the following slides. So besides gravitational lensing and kinematic SE, we also have thermal SE, which is the effect that I showed before. So these are dark spots that we see in our map. So this is basically due to inverse Compton scattering of CMB photons due to electrons in the universe. So these electrons are basically the electrons live in the free electrons live in ionized regions. So these are mostly galaxy clusters. Okay, so hot regions in the universe. So besides these ones, there are also other fainter signals like moving lens effect. There is integrated Sachs-Wolf effect. So these are all much fainter. So I'm not going to go into detail about those things. So now let me discuss a little bit more about KSZ and CMB lensing. Okay, so what is kinematic SZ? So kinematic SZ is a Doppler boosting of CMB photons due to free electrons in motion. So this is very similar to thermal SZ, but the only difference here is that the electrons are actually moving. Okay, so this comes due to two sources in the universe. There is a high redshift source and there is a low redshift source. So the low redshift source is basically due to galaxy clusters. And when I say low redshift, so these are redshift below 3. Okay, so these are local things that we see in our universe. So like galaxy clusters and galaxies, all the halos moving towards each other. So they give rise to the KSZ signal. So we normally call it the post-reionization signal. And these are basically due to matter inhomogeneities in the universe. But then there is a high redshift component, and that is due to patchy reionization signal. So I will explain that in a little bit more detail in the following slides. So, but just wanted to mention here that there are two different sources. So the high redshift source is basically from redshift maybe 6 to 10, and the low redshift source is 3 and lower. So then we also have gravitational lensing. So what is gravitational lensing? So this is basically the bending of light due to matter in the universe. So the light is trying to travel, and then there is basically matter in the universe. So these are due to galaxies, clusters, cosmic web. They are bending the space and time, and so the path of the CMB photon is being deflected because of the presence of matter. So as you can see, these two are excellent probes of reionization, structure formation, and so on. So how do we actually detect these signals using SPT or any CMB instrument? So what we normally do is we construct something called a quadratic estimator. Okay, so the reason we construct a quadratic estimator is because both these signals, so the KSZ and CMB lensing, intuitively they are very similar. So what is happening here is that we have structures on small scales. So there is clustering of matter on small scales, but there is basically a large-scale modulation of the small-scale clustering. So in the terms of when we talk about KZ, this modulation is happening because there is a large-scale velocity flow in the universe. And then for lensing, it's basically because of for CMB lensing, it's basically because of gravitational lensing. So both these effects are very similar. So they are some kind of large-scale modulation of small-scale power, and quadratic estimator, which is simply taking a map, filter the map, apply some weight to the map, square it. That is basically, that is the reconstruction that we would like in terms of for KSE or for lensing. So like I said before, so KSE can probe reionization, it can probe dark energy, neutrinos. There is some kind of degeneracy between cosmology and astrophysics when you talk about KSE. I'm not going to go into detail about that. And then when we talk about gravitational lensing, so gravitational lensing can probe dark matter, dark energy, neutrinos, and so on. Okay. So the other thing that I would also like to mention here is that, so even though we construct this quadratic estimator, this quadratic estimator is actually suboptimal for future surveys. For future low noise surveys, quadratic estimator is a little suboptimal. In fact, it is actually suboptimal even for the next release of SPT3G. So my colleague Marius will discuss some more optimal estimators to extract these signals. Okay. So now let me get into KSE and reionization. So Marius will be talking about CMB lensing. So in the next few slides, I will be showing some of the recent results on reionization from SPT. So before going to that, let me say what this epoch of reionization is. So previously I said universe became neutral at the time of recombination. So this is around 400,000 years after the Big Bang. And then universe remained neutral until first stars and galaxies formed. So what's happening now is that, so the universe is basically filled with hydrogen mostly. But when first stars and galaxies are forming, so the energetic UV photon from these stars and galaxies are basically hitting this neutral atom, and they are kicking an electron out of its orbit. So universe is now becoming reionized. Okay, so this is the second time the universe is ionized. So that's why it's called reionization. And then this process of reionization is expected to be a very, very patchy process, meaning there will be some small bubbles in one location, there will be some large bubbles in another location, and finally those bubbles coalesce to to form bigger and bigger things. Okay, so this epoch of reionization is expected to be a patchy process, and that has some relevance for the next few slides. Okay, so how do we actually probe reionization using CMB? So there are actually multiple ways besides KSE, which again I'll talk in the next few slides. But if you think of reionization and how do we probe this? So basically, it's just the CMB photons are free streaming towards this, but then suddenly when universe is reionized, there is basically this cloud with some opacity. So as the photons are traveling through this, their amplitude is going to get attenuated, so the power is getting suppressed. Unfortunately, though, this power suppression is very degenerate with just the normalization parameter of the power spectrum, so it's not a very good probe. So the other good probe is at the time of reionization, so we have this additional polarization that's being generated around redshift 10. So around redshift 10, the size of the universe was much bigger than what it was at the time of recombination. So what we expect is a large-scale bump in the polarization signal, so both in EE and TE. So we expect that around L of 10, so which is a very, very large angular scale on the sky. So since it's very, very large angular scale, ground-based experiments cannot measure this because we are limited by sample variance. So you really need satellite, full sky measurements for this. The other important thing about this E mode or TE or E bump is that it's not very sensitive to reionization history. So here is a really good example made by Planck collaboration for that. So on the left plot, we are basically seeing the reionization history of the universe. So the horizontal axis is the redshift. Vertical axis is the reionization, so it's the ionization fraction of the universe. So 0 is universe is fully neutral. 1 is when universe becomes fully ionized. Okay, so you can see at a high redshift, universe is fully neutral, but then at low redshift, it is fully ionized. But then there is some transition between going from neutral to fully ionized. There are multiple curves here, but if you take these multiple curves and if we try to determine what will the E mode bump be, they all look very similar to each other, which is shown on the right panel. So even though we have detected this signal, even though we have measured the value of optical depth, we actually do not know much about how the reionization actually happened. So that is why we need to probe, we need to use other probes, like, for example, KSZ. So how can you use KSZ? So the one of the easiest thing to do would be to just compute the power spectrum of the KSZ. Unfortunately, though, measuring KSZ is really hard because KSZ is very faint compared to all the other signals that we have in our CMB map. So this includes the primary CMB itself, and then we also have these signals from dusty galaxies and radio galaxies. So these are all additional contaminations. So it is very hard to detect the KSZ power spectrum. So there are a couple of papers that I've referenced here if you want to look into more detail. Nevertheless, we did make a 3 sigma detection from the previous release of SPT. So we did make a 3 sigma detection of the KSZ. So can we actually say something about reionization using the 3 sigma detection? So it's a little hard, and the reason for that is because if you remember previously, I told you that KSZ comes from 2 different sources, a high redshift piece and a low redshift piece. Unfortunately, when we look at the power spectrum, these 2 things look very similar. So they roughly have the same amplitude and they have the same shape. So if we want to infer reionization physics from KSZ power spectrum, we need to actually know the low redshift component very well. So it's a little hard to do this with just a 2-point function. So that is one reason. So the other reason, again, if you remember, I told you that this epoch of reionization is expected to be a really patchy process. So if something is very patchy, why do we have to limit ourselves to power spectrum measurements? So we can go beyond power spectrum. So this was shown in this paper by Smith and Ferraro back in 2016. So they showed that if you look at the tri-spectrum of the KSZ, we can separate these 2 signals really well, the high redshift piece and the low redshift piece. So the high redshift piece is expected to be extremely non-Gaussian. The low redshift piece, even though it starts out Gaussian, due to the line of sight integration, due to central limit theorem, it becomes very Gaussian. So when we look at the power spectrum, even though they look very similar, when we look at tri-spectrum, they actually look pretty different. So if we actually detect the KSZ tri-spectrum, then we can say a lot about reionization. Okay, so that is the motivation. And then we tried to do this recently with SPT. So here I'm showing the footprint from different SPT surveys. So the one that we have to concentrate is this little green box, which is actually only 100 square degree region. The reason we chose this region is because it has a very good overlap with Herschel experiment, which is so Herschel is a satellite, and it measured so it basically measured the cosmic infrared background, which is basically signals coming from dusty star-forming galaxies. So what we did is we combined data from South Pole telescope, so 2 generations of South Pole telescope, and then we combined it with Herschel. So we used 5 different bands, so 90, 150, 220, 600, and 857 gigahertz. And then we tried to reconstruct the KSZ 4-point information. Okay. So on the bottom left, we see these 2 maps. So on the left is the map from simulation, and on the right is the map from data. And all I would like to say here is that the data and the simulation, they look very similar statistically, which says that we actually understand what's going on in our data. So then on the right, you're looking at the tri-spectrum measurement. Okay. So as you can see, it's a clear detection of the tri-spectrum. Okay. So in fact, it's a 10 sigma detection or 10.5 sigma detection of the tri-spectrum. So again, the horizontal axis is the multipole. When you look at right side, you're looking at small scales. When you're looking at left side, you're looking at large scales. But here, this whole thing is very limited. So this is a very large scale information. On the vertical axis is a 4-point information. Okay. And then when I say 4 points, so this is actually a squeezed 4-point. Okay. So this is a 10 sigma detection of the tri-spectrum. So now if I try to, put a simulation distribution on this, just to make sure that we can quantify the significance of the measurement, this is how they look. So the violence are distributions from 100 different simulations. And you can see that our data matches pretty well with the sims. Okay. So now, if I go into this next one, so I'm showing multiple curves here. So the black curve is actually the expectation from simulation. So it's the mean of all of those 100 sims. And the band is some systematic estimate that we inferred using SIMS. Blue line is it's actually a contamination that we have in our map. So this is basically because of disconnected Gaussian terms in the quadratic estimator. So now if you remember, quadratic estimator is simply squaring the map. So it's some filtering, weighting, and then squaring the map. And when you're doing this, we also pick up these contaminations, but we can measure them well with SIMS. So, so the green points already have this blue line removed. So I'm just showing that here, for example. So now, what are we actually measuring? Are we really measuring KZ here? Unfortunately, the answer is no, because the SIM curve that you're seeing, the black curve, so that is, the SIMs actually don't even have KZ in there. So they don't have the reionization KZ in there. So whatever we are measuring here is basically contribution from CMB lensing and foregrounds. So even though we applied a lot of filtering and a lot of scale cuts to reduce these contamination, we still see them. It's unfortunate. And the reason for this is because the KZ signal is actually very subdominant. So again, this plot is the same as before, but now I'm also showing the expectation from the reionization KZ signal. So the midpoint of reionization is fixed for these curves. So I'm just modifying the duration of reionization. And as you can see, when we modify the duration of reionization, the KZ signal goes up or down, depending on what the value of duration is. So if we take this black curve and subtract that from the green data points, all of our green data points are now going to align close to 0, meaning that we don't have a detection. But it's okay. Even without the detection, we can still set upper limits on the process of reionization, and that's what we did in this recent paper. So what I'm showing here is basically the likelihood for 2 parameters. Horizontal axis is the duration of reionization, vertical axis is the midpoint of reionization. And as you can see, unfortunately, if we just take the KZ 4-point information, it's very degenerate for these 2 parameters. However, from other observations of high redshift quasars and Lyman alpha forests, we know that universe became fully ionized around redshift of 5 or 6. So it's actually called the Gunn-Peterson trough, so which I'm showing here in those blue points. And I'm also plotting all the other high redshift measurements of Lyman alpha forests and quasars here. And the green band is basically the KZ only limit that we came up from this paper. So we do know that the universe reionized around redshift 5 or 6, so fully ionized. So now if we use that information, we get this plot, okay? So the purple line, which I hope you can see my cursor. So the purple line, which is called the GP prior, so that is the Gunn-Peterson trough prior. When we apply that prior, we completely exclude this portion, which is in gray. So then we are left with just this portion here. So when we apply this Gunn-Peterson trough and combine KZ 4-point measurement, we get actually pretty nice constraints on the duration of reionization, which is 4.5 2 sigma. So it's not a detection, but it's an upper limit, 2 sigma upper limit. And then we did various systematic check, and then we found our measurements are extremely robust to CMB lensing and foreground signals. The other important thing about this is that we don't include Planck in this. So we show Planck. We also combine Planck with KZ and the GP prior. But our main result is without Planck, and Planck is shown in blue. So as you can see, Planck does not constrain. Planck does not constrain either of these very well. But our results are very consistent with what has been measured by Planck. So this is the first time that this has been done. Even though we don't have a detection, it is still a very good upper limit, and it's consistent with Planck. So the future, however, looks pretty promising. So here I'm showing information from KZ 2-point combined with KZ 4-point and also Planck. So this is the forecast for different upcoming results from SPT, Simon's Observatory, and CMBS4. So the left panel is for KZ 2-point, middle panel is for KZ 4-point, and the right panel it's a combination of everything. Horizontal axis is the optical depth. Vertical axis is the duration of reionization. And as you can see, the left panel and the right panel have slightly different degeneracy direction. So when we combine them, and then when we also put Planck in there, we actually get pretty good constraints from the future CMB surveys. So for example, from CMBS4 and SPD3G and the next generation SPD, which is called SPD4 or SPD3G plus, the duration of reionization is, the error on the duration of reionization is expected to be 0.5. You can compare this to the 4.5 that we obtained previously, even though that's a 2 sigma, so this is 1 sigma. So this is great. So this is completely unconstrained by Planck. And then the other important thing is that when we combine these with Planck, we also improve our constraints on the optical depth. Okay, so this is great. So the future looks great, even though we don't have a detection yet. So that's KSE. So next is CMB lensing. So I will leave Marius to explain more about CMB lensing.
Thank you, Srini. So now on to CMB lensing. And lensing is a lot like the KSG distortion, but instead of electrons that are scattering the CMB photons, it's actually the photons being deflected by gravitational potential wells. And we can measure the amount of lensing there is at different angular scales and make plots of the lensing power spectrum like this, which is a tabulation from a number of experiments that have measured this effect. And using model fits to these data points, we can learn things about the late time structure formation of the universe, its expansion history, its geometry. These maps are also highly correlated to other low redshift structure probes, things like cosmic shear, galaxy lensing, CIB. And so they're very valuable observable in these cross correlations. In terms of the deepest lensing maps made, that means where the error bars are smallest at the smallest scales here. Those come from SPT 2018 data that are shown in the black points here. And the largest scales are best measured by experiments with a lot of a large sky area that's measured. So things like Planck and ACT. So before diving into some of the results I want to show you, just to get oriented with respect to some of these data sets I'll be talking about. So these are different regions of sky that will be probed by upcoming SPT measurements, ongoing and upcoming. So the solid green here is this 1500 square degree patch. That's our main patch. I've broken it down into the different years that it's being observed, and then furthermore into different spectra that you might use in your analysis from those years. So temperature autocorrelation, E-mode autocorrelation, the cross correlation, and then the lensing reconstruction autocorrelation. So we have some results, like those 2018 results I just mentioned are these. There's papers on the primary CMB spectrum. For this new extra 2 years of data, we're going to have papers on the primary CMB spectra, papers on lensing. And actually the first, the results I want to show you here come from actually the combination of the E-modes and of the lensing spectra obtained from polarization. And then at the end of the talk, I'm going to give you some forecasts on what we expect to get when we throw everything together. We also have the summer and the wide fields here, which observations for those have sort of been ongoing throughout this whole time. And I'll show you what we expect to get by the end. So now this first result that'll be coming from this 2-year analysis with this EE and phi, it's also special in another way, which is that it uses a method for doing the analysis, this optimal Bayesian method called MUSE, that's important now and will be sort of crucial over the next decade of CMB observations. And the reason for that is because it just gets better reconstructions, it gets lower noise. So this is a plot of noise levels relative to the signal CMB lensing spectra that you see here in gray. So you have Planck, ACT, SO, already with SPT observations, which are very deep, but smaller sky than something like ACT or SO, but we're at noise levels that are already below that. And using this method, this optimal method, we can reduce the noise even further from something like the dotted line down to the red line. So it's a factor of maybe about 30 to 40% improvement in the noise. And in the future, with something like CMBS4, at those noise levels, we expect to get almost an order of magnitude reduction in the noise. So these methods are important to see that they work. And additionally, once you do this Bayesian method, it's actually sort of really easy to do this thing called delensing, where you separate out the lensing reconstruction and then separately the original unlensed CMB. And this can give you some slightly tighter error bars on a few parameters. It's also a more useful physical separation of these quantities that are being measured. So these results will do this delensing. Here is an image of one of the data maps that goes into this this analysis. So this is one frequency, 150 gigahertz. It's Stokes Q polarization. This is really sort of the raw data. It's got noise in it. It's been filtered in various ways. A lot of the structure that you see here is indeed the CMB by eye. The full analysis is going to be 3 frequencies, 90, 150, 220, and then Stokes Q and U. We also, of course, have temperature, but for reasons of simplicity, we decided to go for just this polarization-only result to start. And the Bayesian analysis more or less works by just modeling that data as a function of the unlensed CMB, the lensing potential, all the different instrumental effects and systematics, transfer functions, noise, and then just working backwards and doing inference on those quantities. So here is the inferred map of the lensing potential. Actually, it's Laplacian, so this is the kappa map, which is the thing that traces the matter. So you see matter overdensities in red and underdensities in blue. This is the thing that would cross-correlate very well with low redshift structure probes, and we will certainly be doing plenty of that. We can also reconstruct the unlensed CMB. So this is unlensed E modes. You see here. And we can also infer things like the lensed B modes. So this is our lensed B mode map. And this is the kind of thing that would be useful if you want to de-lens another experiment, something like BICEP, which has overlap with this, to remove the lensing foreground for detecting B modes from primordial gravitational waves. So those maps are sort of an intermediate product of this full inference algorithm. It's not quite as simple as just take their power spectrum and plot it, but you do the inference and you get unbiased estimates of the lensing spectrum and of the EE spectrum. And that's what I'm showing here, this result from this paper that's in prep led by Fei Ge. And of course, it's not out yet, so I can't actually show you the y-axis, which would let you draw any cosmological conclusions. But just to demonstrate here, you can see we do detect lensing. We do detect many peaks in the unlensed EE spectrum. And to plot that same data in a different way, this is now showing the ratio to a Planck theory spectrum. Of course, to remain without revealing the results, I've also moved the data points to bang on the theory spectrum, but you can use this plot to compare error bars to some other measurements. And so plotted on here are Planck in blue, ACT in orange, and then some previous SPT results in red and green. So if you focus here first on just the E modes, it's a little bit weird to put on the same plot, but I think still instructive. So the black points are delensed, whereas all the other points are not delensed. They're the primary CMB. But that shouldn't have a major impact, I think, on at this level. And so you can see that really once you get to small scales in EE, these black points are significantly tighter than anything we've had before. And then that translates into better constraints at the very smallest scales on 5.5 as well. And so this is actually kind of a really useful thing because we're probing this cosmological model, ΛCDM, and doing tests of ΛCDM, but now it's through kind of a different physical regime. The physics that affects the very smallest scales in polarization and in lensing are different than the physics that affect larger scales and in temperature that have more dominated some previous experiments. So this is a really valuable cosmological cross-check. And to drive that point even further home, here I've plotted a bunch of models from that have been fit to Planck EE data. So here in EE, they fit these blue data points, but then at smaller scales, they're allowed to vary as, within the model variation. And you can see that, a lot of these are being ruled out at the level of these black data points. We, of course, care a lot about systematics. So the results that you see, I've seen here, they've been marginalized over about 50 systematics parameters. This is the correlation matrix between the band powers, 5.5, and the EE. And then these are the 50 systematics parameters. About 10% of the error budget is systematic in EE. And But in 5.5, actually, only about 2% of the error budget is systematic. You can see that here because this cross correlation between systematics and 5.5 band powers is almost 0. And this is actually kind of a unique thing that's, this robustness is kind of unique to doing this in the Bayesian way, as opposed to doing the naive quadratic estimator, which doesn't propagate things in quite the same without more work, and ends up leading you more sensitive to systematics than you really are. For cosmological results, this is the types of things we expect. Here I'm showing constraints on the Hubble constant, H0. You have Planck and ACT in blue and orange from their full CMB lensing and lensing reconstruction data sets. They obtained this somewhat low value. Shoes, this local measurement of the Hubble constant gets the somewhat higher value. And in black, you can see the level of error bars that we are getting with this data set. Here, I'm obviously not showing the central value, but I've just moved it to be at 70. And similarly, for another interesting tension, the sigma 8 tension, this measurement of the amplitude of matter fluctuations, you have Planck and ACT slightly high values, some lower redshift structure probes, things like DES, year 3 shear, and others slightly low. And so these constraints are really, the errors are right in line with all of these and will tell us some interesting new things about the universe. And of course, the main thing is that it's not just another cross-check of the data or, of the same modes in the CMB. This is really this new regime of small-scale polarization lensing that will be sort of an independent check of ΛCDM. And you can imagine if there's some modified physics that explains any of these or that is needed to explain any of these, it could impact things like large-scale temperature differently than this really small-scale polarization and lensing. Okay, so coming back to this summary of data sets, now let me show you some of the things we expect when we do this full combination of all of this data that we'll have by 2026. So this is a figure of merit plot. So the y-axis is showing you the inverse volume of allowed ΛCDM parameter space. More is better. And the previous slides have basically been showing you results from something that's like this green square at the bottom left. It's actually not even quite this because what I showed you there is polarization only. So with addition of polar temperature, then we get to the green square. And as you go further forward in time, you see more observations of the main field, as well as observations of the summer and of these wide fields will take us to almost 100, factor of about 100 reduction in this figure of, or increase in this figure of merit. And so with data that we will have by 2026, we'll be at about the same figure of merit expected from Simon's observatory, which itself also turns on right around that time. In terms of individual parameters, so that factor of 100 split across about 6 parameters in ΛCDM means we're getting 1.5 to 2 times better constraints than Planck on several of these parameters. And in terms of extensions, the improvement over just Planck, we expect about 2.5 times tighter constraints on things like the neutrino mass, the number of species of neutrinos, the equation of state of dark energy, and some other parameters. So to conclude, we hope that we've showed you that CMB anisotropies are a really excellent probe of various physical effects in cosmology. SPT is really leading the charge in terms of these deep CMB polarization measurements, and in addition to some of our shallower wide fields, we'll have really competitive constraints. Srini talked about the KSC measurements, some of the first constraints on the duration of the epoch of reionization. I talked a little bit about some of the primary CMB cosmology measurements, including giving you a preview of this analysis that's coming out soon, and there'll be several from this 2-year data set as well. This also included a demonstration of this next generation optimal lensing reconstruction and delensing. And from the full 3G survey, again, we expect 1.5 to 2 times better constraints than Planck for ΛCDM and extensions. We'll be at about 2 years of Simon's observatory figure of merit and complete that in 2026. And beyond all of this, there's also many other different analyses that are coming from this rich data sets, which we're excited to get out there. So thanks on behalf of me and Srini.